Today's lesson is part 2 for section 2.5 in your textbook. So we're picking up where we left off yesterday. Yesterday we talked about and went over rigid transformations. So we talked about horizontal and vertical shifts as well as reflections. Today we go on into the last part. So if you turn to page 209, you would be on the non-rigid transformations with me. So the things that we're going to look at today, the reason that they are called non-rigid is now the transformation to your function is going to change the basic shape of that function graph. Okay, so yesterday with the rigid it didn't, it just kind of moved it. Today it's going to be shrinking or stretching. All right, so vertical stretches and vertical shrinks. These are found or created if you multiply the entire function by a constant greater than 1. That will cause your function to stretch. All right, we'll go through some examples to demonstrate that here in a second. A vertical shrink will happen if you multiply the entire function by a value that's between 0 and 1. So in other words, you're going to be multiplying or using a decimal or fraction in that function, which will cause the shrinking to happen. These are going to be so much easier to understand, I think, or at least somewhat easier to understand if we look at some examples. Horizontal shrink, horizontal stretch. Again, we'll look at examples of these in a moment, but a horizontal shrink is if you multiply only the x part of the function. So we're going to be inside that function again, only on the x, by a constant greater than 1. A horizontal stretch is if you multiply only the x part of the function by a value between 0 and 1. So you can see some similarities between these vertical and horizontal shrinks and stretches. And they will, again, mess with the shape of our graph. They're going to shrink and they're going to stretch. So I would equate that to getting skinnier and getting fatter, or maybe kind of modeling the looks of a rubber band if you pull it. So anyway, let's take a look at just diagnosing a few or describing a few of these transformations first. Then we'll go on and we'll take a look at some graphing. This first one up here, okay, notice that you have a 3 times your parent function x squared. So with having a constant greater than 1 multiplied to our function, we have a vertical stretch of times 3. Okay, the next one. Again, our constant or our multiplier is in front of the entire parent function. We've got 1/3 x squared. But with the multiplier this time being a constant between 0 and 1, we've got that fraction 1/3. This is the one that results in the vertical shrink. The third one on the page, now our multiplier, notice, is attached to the x part of the function only. It's inside there on the x. That is what results in a horizontal shrink. Okay, and I'm going to kind of describe that in a little bit more detail. I think this will help us simply because the shrink on this one, when we're talking about horizontal, we're talking about width. All right, so that horizontal shrinking is 1/3 the width. Okay, again, that'll be a little bit more apparent when we look at some graphs. The last one then, the final one, we've got 1/3 multiplied to just the x portion of our function. So again, we're looking at a horizontal one. This is what a horizontal stretch will look like. Okay, so horizontal stretch of times 3. Okay. All right, let's move on. So I've started it off with, on our picture of our graph here, I've given us the parent function of x squared because that's the one that we're going to be playing with with these transformations that we're going to do. So letter A, first of all, g of x is equal to 4x squared. So notice we have a constant that's greater than 1 multiplied to our entire function. So I'm looking at a vertical stretch on this one of times 4. Well, let's just do a few table of value points and do some graphing so you can see what that vertical stretch looks like on the graph paper. Okay, so the points that were graphed were at 0, plus or minus 1, and plus or minus 2, you know, your regular parabola x squared function. So I'm going to stick with those same inputs with our new function. So if we put 0 in, we get 0 times 4, which is still 0. If we put in a negative 1, we're going to square that and get positive 1 times 4 is 4. Putting in positive 1 will give us the same. Putting in a negative 2, we're going to square that, and that'll make 4. 4 times the front 4 gives us 16. And a positive 2 will get the same. So let's graph this one and take a look at what the picture does. So 0, 0 is still there. But now negative 1 is up at 4. Positive 1 is also at 4. And then negative 2 and positive 2 are way off the chart. They go way up to 16. So we can just tell that our graph is going to do this. Okay, so take a close look at this. This one was called the vertical stretch. Do you see that it was stretched tighter? So it's skinnier because it goes up vertically faster. It's stretched vertically. Okay, now let's take a look at h of x for letter B. We've got 1/4 x squared. So doing another table of values here, and again, I'm going to stick with those same inputs. If I put 0 in, I'm still going to have 0. Oh, and I think I'm going to change the color. Okay, we'll do the second one in green. Putting in a negative 1, I'm going to get x squared will give me positive 1 times 1/4. So I'm going to get out of 1/4. Same if I put in the positive 1. If I put a negative 2 in and square it, I get 4 times 1/4 is 1. And the same thing happens if I have my positive 2. So graphing this one, 0, 0 is still a point. But then negative 1, 1/4. And positive 1, 1/4. 2, 1, and negative 2, 1. Take a look at what it does to the shape of your graph. Okay, so this was a vertical shift again, but notice how it got fatter. So if you're speaking vertically, it shrunk. It got higher, slower, or it got flatter. So it shrunk vertically. All right, so by widening it out, we shrunk it vertically. Hopefully that makes sense. Let's go on and do the same kind of thing with our horizontal ones. All right, so looking at g of x for letter A here, and again, I'm sticking with that x squared parent function just for this demonstration. You can see that the 2 in g of x is multiplied to the x only, so we know that we're looking at a horizontal shrink. Okay, so let's play with a table of values here still. I'm going to stick with those same 5 inputs that we've been looking at. And if we plug them into here, we're going to have 0. And if I have negative 1 in there, we're going to have 4. Positive 1 is 4. 2 is 16. And negative 2 is 16. Okay, let me demonstrate that one a little bit better. If I'm putting f of 2x in, do you guys understand that that means that I'm putting 2x in and squaring it? Okay, so 2 times negative 1, the 0 one, I figure you guys have that. 2 times negative 1 is negative 2 in there, but then I square it. So that's what resulted in my 4. And then the positive 1 would do the same. Negative 2, if I put that in there. Okay, so again, I'm looking at plugging 2x in for my x squared, I get a negative 2n times 2, so that's negative 4, and I have to square it, and that's where the 16 came from. Okay, so if I have f of 2x, we know from our previous sections that that's telling you to stick 2x in for every regular x of the parent function. Okay, so hopefully you're following me through that. Now let's look at the graph. Okay, remember I'm looking at a horizontal shrink, so I want to kind of determine or decipher what's happening horizontally, so sideways. So 0, 0 is on the mark here. Negative 1, 4 is my next mark. And 1, 4. And then again, the 16s are way off. So notice that my graph looks very similar to the one on the previous page that had my vertical transformations. But remember, I'm talking horizontally now. So width. How did the width change? Do you notice how the width got much narrower? It shrunk. This one is a horizontal shrink. Okay, it is half as wide as it was before. So that's why when we describe this one, horizontal shrink of a half. Okay, and you can see that I think the picture helps out seeing that a lot. It's half as wide. It was a horizontal shrink of a half. All right, let's go on to the h of x one. Again, I'm going to quickly fill in the table of values that I chose, sticking with the same inputs again. And these would be the resulting outputs. A 0, 1/4 for both of the 1 and negative 1, and putting in the 2's, I get out 1. Oh, I wanted them in a different color. I'm going to switch over to blue real quick here. Forgot to change pens again. All right, so graphing, the 0, 0 is still there at the origin. Negative 1, 1/4. Negative 2, 1. And likewise on the other side. Notice again the similarities to that one graph that was on the previous page with the vertical transformation. But since we are looking at a horizontal transformation, because our 1/2 was multiplied to just the x part of our function, we want to describe this in terms that talk about horizontal change. All right, so this one is wider horizontally. So it is a horizontal stretch of times 2. It is twice as wide as the parent function. It horizontally stretched twice the width. Okay, so horizontal stretch of times 2. Okay, I wanted to pick one off of our homework page just to guide you through, because it was a 4-part kind of deal that it was asking you about. Part A, if you guys turn with me real quick, that page is number 211. All right, so 21 is at the top of page 211 on the right-hand column. G of x is equal to 12 minus x squared. All right, so our parent function is the first thing that we are asked to identify. Well, with that x squared as part of our g of x, we know that our parent function is going to be f of x equals x squared. All right, I already have that same picture again imposed in our graph, so you can see the parent function in purple off to the side there. All right, letter B asks us then to, in words, describe the transformation. All right, well, there's a couple of things going on here, and it's going to blend in a little bit of what we talked about with our first half of 2.5 from yesterday. But do you see that there is a constant? We have a 12, and it's a positive 12. All right, so our constant of positive 12 says that we're going to shift up 12. All right, remember that constant added or subtracted as a vertical shift. So we're going up or down. Since it's a positive 12, we'd be going up. Then there's also that negative out in front of the parent function part. Okay, so that negative out in front of your parent function is going to be a reflection over the x-axis. Okay, so it's going to do both of these things. We're going to reflect over the x, and then we're also going to shift up. Letter C in this homework section asks us to sketch the graph of g. All right, so we've already got the parent function sketched, so we could potentially kind of count this off, which isn't a bad idea to do. I still like to have a table of values for you guys to look at so you know exactly which points that I have plotted. So I'm just going to provide you with my table that I generated. I stuck with kind of these same numbers that I've been using. And when I put a 0 in, I got out a 12. When the 1s went in, I got out 11s. And the 2s gave me 8s. Okay, so again, I'm using the g of x function. So 12 minus x squared was how I determined those y values. Plotting. So 0, 12. Way up there. And 1, 11. So on both sides of it. And 2, 8. And negative 2, 8. Now I want you guys to take a look at that for a second and go back to where we described our transformations. Now we reflected over the x-axis and then we shifted up 12. All right, now I want you to think about if I'd have done that reflection first. Okay, flip it over the x-axis, know how it would have done this. And then it shifted up 12. Did we raise 12 from every reflected point? And the answer to that is yes. You can see it. Okay, so I'm going to take that back out of there and clean it back up. But when you're done with your graphing, you should be able to go back and see those transformations on your picture. And I think you can tell that it was flipped upside down and then it was raised 12 units. Okay, so you can see both transformations that were in this one. Letter D, it says to use function notation to write g in terms of f. All right, well, that's not really a huge deal. Using letter A here, we know that f of x is equal to x squared, right? So if we're going to rewrite this in terms of f, I no longer want the x squared piece in there. I want the f chunk in there instead. So rewriting g of x in terms of f just looks like this. Okay, so it's a substitution. Okay, substitute out the x squared parent function for the f of x function notation. Okay, that finishes off part 2. So now we should be able to take a look at some problems from pages 210 through 212. So come see me if you had any questions on this. We can do a few more. I know some of this is a little bit hard to wrap your head around, but we can get you there.